Good evening. It's 19:02 by my clock. Uh, we'll start in about 3 minutes to give everybody else a chance to sign in. So 3 more minutes and we'll get going. Presentation takes about 40 to 45 minutes. So thank you for coming. I'll see you in a couple of minutes. All right. Good evening. We're going to go ahead and get started. FYI, everyone is muted. Um, there are fewer people here than I expected. So I think we might be able at the end to try to have some conversation or answer some questions if it gets to that. The other thing is you need to know in advance that I'm an old man playing with new technology, so you'll have to forgive me if the technology does not work in my favor. So stand by and I will try to get this presentation to working. All right. Tonight we're going to talk about some things that your Ventus Pro 3 gas meter doesn't know, or the alternate title is When to Get Nervous, because there are certainly some situations that you're going to encounter that should give you the willies. Um, Interestingly enough, after this presentation ran, um, we've run a pretty serious sulfur dioxide leak in Company 23's area that highlighted some of the things that we talked about here tonight. You can expect some follow-up discussions in a similar format based on some lessons learned from that event. Um, and again, as we go through this, there may be some time to discuss some of those things. So tonight's discussion is framed around an actual call that happened in Montgomery County. There are two instances of almost the exact same call that I know about. And hopefully in discussions with you guys, and if you make use of the feedback tool at resource700.wordpress.com, provide some feedback, we might find out that this problem is a little bit more widespread than we thought. So in the case study, it was about 1900 hours on a weekday, I believe it was. It was the situation was there was a call for an activated CO alarm in a garden apartment. That kind of helps you to have a idea of how big the living spaces are in terms of volume. That'll play in a minute. The only gas appliance in the structure was the stove. No one was reported to be ill. As a matter of fact, the occupant of the apartment met the fire department outside. Everybody was fine. No known issues. It's just her CO monitor was going off. The crews went inside, investigated. No issues with the stove. Uh, but the CO alarm was going off. So they dug around a little bit more. And then they found a back bedroom. The room was about a 10 by 10 bedroom. They had their Ventus Pro 3 gas sensor. or meter with them with the three sensors. And these are the readings that they got. The oxygen level was 20.6. The LEL was 3%, and the CO level was 30 parts per million. These numbers are not 100%. They're not based on the data log. But they're close enough for government work, and they closely approximate what was found. And as we go through this, you see that there's three big questions, and I see some people are on the phone, so I will actually read the questions for you. What's the biggest concern with the numbers you see here? Which one gives you the willies or makes you worry? If you're nervous, well, what are you nervous about? And based on what I've told you so far, answer the question to yourself honestly. Is that enough to make you put your SCBA on? Well, before we answer some of those questions, we'll talk a little bit about sensor technology. And the sensors that we use some pretty basic chemistry. And I'm trying to tell this story without going into all the details. But inside that little sensor, and that's about how big it is, that's actually an MX6 sensor you see on the screen. They are basically small batteries that take in gas. The gas diffuses across a membrane, and in our case, is drawn in by a pump. There's some chemistry that happens, right? I'll just leave it at that. That chemistry produces an electrical charge. That charge varies depending on how much of the target gas is present, and it is displayed as a parts per million concentration. The LEL sensor, the second of the three sensors, also uses electrical current to determine the concentration of flammable gases, but it uses a different kind of technology to do that. And instead of getting a readout in parts per million, you get a readout as a percentage of the lower explosive limit. And I think it's important to say to you guys here, it is a percentage of the lower explosive limit, such that when the LEL sensor reads 100%, that means you're at the lower explosive limit for methane. And that's because the sensor is calibrated to methane. The third sensor we have is an oxygen sensor. And this is pretty important. We'll spend some time here. Again, some funky, cool chemistry is happening in the sensor. And each one of these sensors, the chemistry actually operates on the surface of the sensor. And there is a thin film of a chemical paste, so to speak, that's on top of the sensor. And that sensor, or those sensors engage with the chemicals that come across it, produce those currents, right? I go back to that to say that the sensors can, over time, use up the chemical substrate that's there, and that does some funky things to your meter readings. Sensors have a life, and in our case, the shortest lifespan is the oxygen sensor. It only has an effective life of about 2 to 3 years. The other sensors are in the same range, but they do last a bit longer. Interestingly about oxygen is that the air that we breathe is 78% oxygen, right? Or correction, 78% nitrogen. And it's about 20.9% oxygen by percentage of volume, right? But math gets a little bit easier if we just say that it's 80% nitrogen and 20% oxygen. So we'll say 80% nitrogen, 20% oxygen. And we'll say that when some substance displaces oxygen, that the nitrogen goes along with it. And that's interesting because at the end of the day, for every 0.1% drop in the oxygen level, that means that 5,000 parts per million of something else has taken its place. And for those of you who might be interested in seeing the mathematics of how that all worked, simply leave a message on the feedback site and I'll share with you the gory details. So, when you see your oxygen level starting to drop in your sensor from 20.9, now, before I say that, it is not uncommon to see some fluctuations between 20.9, 20.8, even 21% oxygen. There's some normal fluctuations in environments, and we'll talk a little bit about some later about some other things that affect it. But generally, when you see your O2 readings dropping, it only means one of two things. Some chemical is replacing the air volume, right? So think about propane. Propane's heavier than air. There's a propane leak in a basement, or sulfur dioxide in the case of the 23 coil. It's heavier than air. It starts to fill up the lower spaces of the basement or the first floor, and it pushes the oxygen and the nitrogen out. You start to see drops in your O2 readings. The other things that can cause the oxygen reading to drop are chemical processes that consume oxygen. The two biggest examples are rust, and you will see this inside of like concrete trucks or steel containers, sea containers, where there's especially if they're sealed up pretty well, where the oxidation process, which is what rust is, right? It's an oxidation process, will consume the available oxygen. And because there's no airflow, you'll see the oxygen levels go down. And concrete curing, part of that process, draws oxygen out of the air for the curing process. And we have seen this in parking decks in Montgomery County. A place for you to be kind of concerned is when we are doing or you see work being done in the parking decks that are relatively enclosed, and it's large concrete work, especially the ones like in the donut construction where there's very little ventilation or interaction with the outside air. It is a point of concern. The next big thing to talk about is cross sensitivities. So in the beginning, I said, listen, guys, there's this chemical paste, for lack of a better term, that's sitting on top of a cylinder, and the gas is drawn to it from the outside air into this sensor, and the sensor does some chemistry. Hold on a second. I know there's some ambient noise, and I apologize. The sensors are not people; it's chemistry. So if the chemical that comes in behaves chemically like carbon dioxide, for example, then there will be similar chemical reactions, a similar electrical current will be produced, and your machine will display a parts per million of carbon monoxide, even when there is no carbon monoxide in the space. So when we talk about carbon monoxide detectors, uh, they are also great acetylene sensors, almost 1-to-1 for acetylene, and they're really good hydrogen sensors. They're okay with acetone, and they are somewhat adequate at picking up volatile organic compounds. You'll see the hydrogens. Well, there was a case in Montgomery County with acetylene where a plumber had been doing some work. The CO alarm went off in the people's house. The fire department comes. They investigate. They can't find a source of CO, but they are getting carbon monoxide readings. They investigate. They find that the plumber left the oxyacetylene torch valve cracked, and there was acetylene leaking into the space. Now, that was a long time ago, so I don't have accurate meter readings, but we would have also expected in that situation to have seen readings on the LEL sensor because acetylene is flammable. Where we see the carbon monoxide detector go off a lot where there's no carbon monoxide is when it's acting as a hydrogen sensor. There are a ton of lead acid and lithium ion batteries and energy systems throughout the county, and we've run numerous calls where those batteries overheat. So typically what you see in that situation is there is a sulfur type odor which initiates the call, unknown odor or inhalation emergency. When crews go to investigate, they get about 30 or 3 to 400 parts per million on carbon monoxide, 3 to 400 parts per million on carbon monoxide. They get about 2 to 3% on the LEL sensor. And for those that are equipped with hydrogen sulfide sensors, there will be some small readings on the hydrogen sulfide sensors. You find those in the battalion car, the safety car, and on the hazmat unit. And what happens is when these batteries overheat and off gas, they off gas hydrogen, and that CO sensor is not hitting on carbon monoxide, it's hitting on hydrogen. Okay? So, the other big point to bring out here is sensor recovery. So we pulled the data logs from the sulfur dioxide instance in Rockville last week, and the ammonia sensor on the hazmat meter went into a negative overrange. So instead of the numbers going up in a positive direction, they went down in a negative direction, and they pegged out. They stayed there pegged out for about 25 to 30 minutes before the sensor began to recover. So it is possible to oversaturate your sensors. And another thing to consider with cross sensitivities is as the sensors age, the number and the effect of cross sensitivities increases with age. So the key takeaway for you guys here is remember the sensor's not smart. It doesn't know what it's measuring. It just knows that whatever chemistry is happening is producing an electrical charge. When I see an electrical charge of that size, I give you a number. Okay? It doesn't care. The other takeaway is that you can overrange or overexpose your meters. And that is another reason why you should let them run for 20, 30 minutes after exposure so that they can kind of burn off that extra chemical and reset themselves. There are a bunch of other things that can impact your sensor readings. This stuff is super interesting, and we could go hopefully one day into a ton of detail. But humidity is a big thing. Humidity is nothing but water vapor in the air. And water vapor is a chemical. It interacts with the sensors. In the case of condensing humidity, that is humidity that forms water droplets. Those water droplets can actually block the intake of the sensor, preventing it from working. What's the takeaway from you there? The takeaway for you there is you have to be really careful as we move into the winter time about taking your 4 gas or your 3 gas, warming it up outside in the cold, and taking it immediately in the house. And if your glasses or somebody on the crew has glasses, if your glasses are fogging up, your sensor is probably being impacted by humidity. And what should you do? You should probably slow down and give that machine a chance to recover before you start investigating. Another big thing is tubing. So depending on what you read, tubing can affect two basic things. One, it takes time for the air to travel through the tube to the sensor, between 1 and 2 seconds extra for every 10 feet of tubing. The other thing that happens is that the tubing can actually absorb gas, and it depends on what type of tubing. There's 3 or 4 basic types, but the hazmat rig actually should have different types of tubing based on how they anticipate or what they anticipate sampling to help to avoid this problem. Tubing can also begin to accumulate gases in the tubing that kind of linger there afterwards and affect your sampling. So if you have tubing, that tubing shouldn't be any more than 10 feet. you have to add time, and we'll talk about response times here in a minute. But you have to add to your response times for the machine once tubing is in place. And don't just grab any old tubing off a fish tank, stick it on the end of your meter, and think it's going to give you good answers, because it won't. Age, as sensors age, they become more cross sensitive, and they start doing this funny thing where they will still pass the calibration, but they won't be as efficient as they were. There are numerous things that can poison your sensor. So what does it mean to poison your sensor? It means to ruin, essentially it means to ruin the chemistry. So expose it to something that will fundamentally alter the chemistry happening at the cylinder level, right, on the sensor, so that it doesn't work anymore. The most common sensor poison out there is silicone-based products, and that includes the fireman's favorite toy, which is Armor All. I beg of you, never, ever, ever, ever use your gas around Armor All, or spray the compartment that the meter lives in, because you've effectively killed it. And if you are in someone's house when they have recently used silicone-based caulks, the same thing will happen. Lack of calibration is a big deal. Sensors will drift with time, and calibration corrects that drift. Uh, Based on what I know and our discussions with Hazmat and the meter shop, calibration compliance seems to be pretty good. So, or pretty good in general. And then obviously we talked about cross sensitivities. So what we talked about was a scenario. We talked about a little bit about sensor technology. It's time to go back to that scenario and just kind of take a look at what was going on. When the crew investigated the CO alarm, went to the back room, this is what they found. It's not that exact model. This is just a picture from Amazon. But the homeowner was using peppermint oil and eucalyptus oil in a diffuser in the room with the door closed, running at full tilt, um, consistently and constantly, in an effort to scare away or repel rodents. And the other situations I know about in the county, the common theme is people using essential oils to repel rodents. So let's talk this through. We had 20.6 LEL, or 20.6 on the oxygen. Where does that come from? Well, the diffuser is pumping out aerosols, materials into the space. The door was closed, right? It's a relatively small volume. It is not unlikely that there was a significant amount of oxygen displacement occurring in that room. There was enough oxygen in that room, right, that you wouldn't notice a difference if you lived there, and it probably wouldn't have bothered you, except for if you were an asthmatic and or someone who was sensitive to all those particulates. But that goes a long way to explaining why the oxygen content was changed. So why were you seeing CO readings? And that's pretty interesting, right? So the CO sensor has some cross sensitivity to VOCs. The oils are volatile organic compounds. That's what makes it able, so they'll diffuse across the room and you'll smell them. And the oils are hydrocarbon based. It is quite likely that CO alarm was a reaction to the VOCs in the peppermint oil and the eucalyptus oil. Furthermore, there's some things to think about. The essential oil market is, it's crazy, right? So real essential oils are really, really expensive. what you find at Target and Walmart tend not to be real essential oils. They tend to be much lower grade and they tend to be cut deeply with alcohols. Okay. Um, LEL sensor. We were getting some hits on the LEL sensor, like 2-3%. Again, that's highly likely that that's tied into the VOC count, as those volatile organic compounds are traveling across that LEL sensor. There's a combustion process that happens in there. And because of the nature of those chemicals, they're able to burn. The response rate is not linear. So you can't say, oh my God, there was this concentration of VOCs in the environment. But that explains to a certain extent the LEL range. And unfortunately, we are at a point where sensor age starts to play in because these Ventus meters have been out there with the original sensor set now for a couple of years. And again, as the sensors age, the chemistry changes, cross sensitivities increase. So you got to think after that. I think there's some core lessons that are applicable across our space and that we should consider. You have to think through the hazards. You have a 3-gas sensor, and I don't know if we've ever talked about it like this, but it's a 3-gas sensor. The sensor market, I will tell you, is not designed for the fire department. There aren't enough fire departments in America that make it worth anyone's while to build a sensor for firemen. These sensors are built for, and I keep saying firemen, I meant firefighters, so my apologies. But these sensors are built for industrial applications and in most cases for mining, or a lot of cases for mining. And why that matters is if I'm working in an industrial situation or in a mine, I have a much better idea of the chemistry of that environment, and I can buy and design sensors that work really well in that environment. And you can actually buy sensors that reduce cross sensitivities using different charcoal filters and different chemistry. But for this mass production sort of thing, general purpose, that's just not practical. So when you think about your sensor arrangement, think about it in terms of 3 big things that one should be worried about. I have to be worried about toxicity, those things that can kill me. We only have one real tox sensor in that meter, and it's carbon monoxide. And while carbon monoxide may be cross sensitive to other stuff, don't ever think for a second when you're investigating an unknown odor that because your CO meter went into an alarm, that means definitively the CO is there, or because it didn't go into alarm, that somehow means nothing is there. Okay? The other tox meter that we have, or tox sensor that we have, is oxygen. And that goes back to that notion that every 0.1% drop in oxygen represents 5,000 parts per million of something else. What's the something else? I don't know, but I get a zero point 0.2 drop in my oxygen. There's 10,000 parts per million of something else. I encourage you to think about which chemical on earth you would want to breathe 10,000 parts per million of, other than nitrogen and oxygen, right? So we can use the O2 sensor um, to as a very broad band toxicity sensor. My apologies. I thought I turned off the chat function. I meant to do it, and I will beg all of you to refrain from using it because it's a pretty big distraction. The second big hazard category that we use the sensor for is asphyxiation. Now, the alarm on your Ventus is set for oxygen. The oxygen alarm is set at 19.5%. That, again, is based on industry practices, and that is about the oxygen percentage at which you will start to see deleterious effects on your mentation, or you stop being able to function. You still have room. It's still a nice buffer between there and a concentration of about 15%, where you'll start not being able to function or escape. But the second big threat is asphyxiation. The third big threat is blowing up, right? So your LEL sensor tells you how big you are or how close you are to an environment where it's possible to blow up. Now, our sensor is calibrated to methane, which is the primary component of natural gas, and it is set there for a reason. It is a one-to-one read for natural gas because that is the chemical that we use it for overwhelming majority of the time. We used to calibrate to pentane many years ago. And when you ran a natural gas leak, you had to do some mental calculations to convert from pentane to carbon monoxide. And the reason the pentane was chosen is because it was kind of a middle of the range sensor. So it would catch up and alert you on a lot of stuff faster. We believed that the safest bet was to switch to methane, which we did, I think 5, 6 years ago, maybe, and to stick with methane because we wanted a one-to-one on the chemical methane that we came across most often. You'll see of all three of these sensors, the only one that has an impact on all three categories is the oxygen sensor. So let's talk a second about the impact of oxygen on LEL. Again, I told you that in the LEL sensor, there is a combustion process going on. That combustion process requires oxygen, right, to oxidize the material in the sensor. When the oxygen saturation or when the oxygen percentage gets below 15%, that LEL sensor is no longer reliable. There's not enough oxygen, free oxygen in the air to support the combustion process reliably. You can no longer trust that. What's interesting is that's about the same level of oxygen, 14, 15%, that is required for flaming combustion. So when you see a plume of smoke that is obviously warm enough to flame, it has enough fuel to flame, which part of the fire triangle is it missing? It's missing the oxygen. So when you see thick, dark smoke pumping out of a room and no flame, you have a pretty good idea that the oxygen concentration in that room is less than 14%. Lesson number 2, when you see changes on more than one sensor, the hair on the back of your neck should stand up. We do carbon monoxide leaks, got a sensor for that. We do natural gas investigations, we got a sensor for that. If we're investigating a natural gas leak and you start seeing changes in your carbon monoxide meter, that should cause you to pause and say, what on earth would make that happen? Likewise, if you're investigating natural gas and you see changes in your oxygen sensor, you have to ask yourself, what is making that happen? Policy doesn't dictate this, but it is something for you to consider. And I'm not going to make policy declarations tonight. But if you're on a run and you see sustained changes from normal in more than one sensor, that is a strong indication that you should at least pick up the radio and do a consult with the hazmat team. The next lesson is, well, where and how you look matters. So it really does matter. What you find depends on where you look and how you look. We, being the fire department, go to investigate an odor or report a gas or whatever, and we start thinking about these things in terms of treat them like they're homogeneous spaces, and they're not. So, what do I mean by that? If I have a carbon monoxide leak in the house, there will not be an equal amount of carbon monoxide distributed throughout the house in the entire volume. There are going to be pockets with higher concentration, pockets with lower concentration. Carbon monoxide has a vapor density of 0.97, where air is 1. So it is slightly lighter than air, but I call it buoyant. It's essentially buoyant. It mixes with the air. Okay, it's there. But again, the concentrations are not linear and they're not consistent throughout the entire space. Propane, sulfur dioxide, much heavier than air. Hydrogen, much lighter than air. So it is possible to walk into a house, have a significant leak of hydrogen because batteries are off gassing, and not find it on your meter or your sensors because you're holding your sensors at waist level, right? And by the time there's sufficient hydrogen in a space that, as light as it is, that you can see it on a sensor at waist level, it probably blew up already, right? Well, with propane, it's the opposite. So we had a call in 23's area years ago, and I arrived, and there's a special service crew, and they're at a propane leak. We had a large refill station at a gas station with a propane filling station, and it was leaking. And the crew was there, and they were quite casual, and they had their four gas, and there was nothing visible. And I walked over, so what are you doing? And they said everything's fine, and they showed me their meter. Yeah, they had 0% of the LEL. Nobody was wearing SCBA. Nobody had their structural PPE on. And I simply asked the guy to lay a sensor, lay your meter on the ground. It was an alarm before it hit the ground. They were at probably 50 or 60% of the LEL outside. And while you say, okay, we're only at 60%, it's not going to blow up. Remember, uh, the conflagration or the deflagration comes when it hits an ignition source, and it only has to be within the flammable limits at the ignition source, and that flame front will propagate out to you, consuming fuel towards you. So those guys were walking in an invisible time bomb unprotected. Why? Because they were looking in the wrong space. So this is also a good time to talk to you about sensor response times. You'll see on this slide, it tells you that the 90% response time for oxygen on our sensors is about 30 seconds. So in an environment where the oxygen concentration is known, it takes our sensors about 90 seconds to register 90% of that concentration. The total response time, we say, is so that's the T90. The other measurement you'll see a lot is the T50, and it's a trick. The manufacturers report the T50 because it makes it seem like their sensor response time is faster, but that's how long it takes for it to register 50% of a known concentration. Most of our sensors, from LEL to carbon monoxide to oxygen, have a 15 to 35-second response time. And what that means is, gentlemen and ladies, you can't just walk into a room with your meter at your waist looking at the numbers and walk from the front of the house to the back of the house. By the time the alarm goes off, you're at the back of the house. The dangerous concentrations are 15 to 35 seconds behind you. This calls for you to move slowly and methodically through the spaces, understanding that. The other thing I would like to impart to the listeners tonight is I want you to imagine what a softball looks like. A regulation softball, right? And understand that the Ventus Pros pump pulls in a volume of a regulation softball every minute. So if you stuck the softball on the end of your meter, it sucked all the air out of it. It would take that meter 1 minute to suck their air out. Stand in the room for 1 minute investigating an odor or a leak, and you've only cleared an area or a volume the size of a softball. And it's going to take you a minute to do that at a sensor response time of 15 to 35 seconds. If you take nothing away from tonight, you take away the fact that the O2 sensor is important. You take away the fact that changes on more than one sensor are scary. also take away the fact that you have to slow down. You are walking faster than your machine can process information. As with everything, context means a lot. So the old saying goes, when you hear hoof prints or hoof stamps or whatever the word is for the noises that hoofed animals make when they're running, you should think horses, not zebras. Tonight we talked about horses. For our sensors, carbon monoxide and LEL, especially when we're dealing with natural gas, when those sensors are alerting and moving in a positive direction, it makes sense to think horses. When you have changes on more than one sensor, it's time to start thinking about zebras. And zebras are sort of like those weird one-offs, once in a lifetime sort of things. The plumber who left the acetylene torch is an example of a zebra. Now, there's another thing called a unicorn, right? My boy tells me all the time they don't really exist. I'm not sure. But I do believe that there are unicorns, and I believe that the sulfur dioxide incident in Rockville wasn't a horse, wasn't a zebra. It was the stinking unicorn, and there's some other unicorns out there. And the neat things about unicorns is that you've never caught one. You can go to the zoo and see a horse, go to the zoo see a zebra, can't go to the zoo and see a unicorn. So I use that to represent situations that are really difficult to pin down and where we use what are called orthogonal methods in Meterland to pin down what the source is. It's another great reason why the hazmat team, I believe, should be running more calls than it does. The fire department's really good, the regular fire department with horses. If you're lucky, you might be all right with a zebra or two. You're not going to be able to track down a unicorn. So, what do I mean orthogonal? So the way we figure stuff out in the hazmat world is we use a wide range of tools, meters, and technologies. We still start with basic litmus paper that you can buy anywhere, and changes on litmus paper can tell me a lot. I go back to the example of the sulfur dioxide call. If I pre-moistened litmus paper and walked into an environment with high concentrations of sulfur dioxide, I would have seen that litmus paper change colors to indicate an acid and then go back to white based on the bleaching effects of the sulfur dioxide. It would have given me a good hint. We don't carry that on fire engines. The other thing that they use that night and that they have are chemical or chips. They are chemical reagent chips. They're little glass vials with reagents in them for specific chemicals. Cross sensitivities are markedly improved, but you guys don't have those. And then we have different meters and like photoionization detectors and direct read meters for a wide range of chemicals on the hazmat team. And so when you bring those guys together, what we can do, or what they can do, because I'm not there anymore, is they can say, based on this change in hydrogen sulfide, along with the change in LEO and the change in phosphine and the change in X, and this what I'm seeing on the chip reader, the chemistry of this substance supports that it's sulfur dioxide and not methyl chloride, right? So while they may not be able to do a direct read, they can use, it looks like a Venn diagram as they start piecing the puzzle together. And then I added a picture of mice. I think it's important that horses, zebras, unicorns, and mice, and all the situations where we have come across these situations and similar meter readings, it's because people were using essential oils to repel rodents, and it has happened twice in recent history. It's probably happened a lot more. We just didn't recognize it. So go back to your context. If I'm searching a multifamily dwelling in areas where, or in structures where rodents are problems, that is certainly something to add to your list of things to look for. Another big lesson, we've talked about this already. I always do this and write a slide and then get ahead of myself, but it's worth saying again, speed's not your friend. You gotta slow down. And uh, we are working diligently as an organization to refine our hazmat SOPs, incident response policy. We see this problem. You cannot treat a hazmat call like you treat a box alarm. You have to move slowly. Now, there are things that we talked about earlier that can kill your sensors. And when your sensors die, they look great because they fail at zero. They say, oh, there's 0% LEL, there's 0 parts per million of carbon monoxide. And how do you kill them? Use a near a silicone-based product. You kill them with alcohol. MCFRS did a fine job in March and April of this year of destroying about 50%, maybe 60% of our carbon monoxide meters with overzealous firemen wiping them down with alcohol. The alcohol kills the sensors. Now, most sensors can recover from alcohol poisoning, but when it happens every day, we ended up replacing a whole lot of sensors. And high concentrations, even of the target gas, can kill the sensor. And you now understand the mechanism for that. The chemical gel on the sensor just runs out of reagent. There's nothing left to react with. Oh, one more point about failing to zero. When people are sick and your meter reads zero, don't be so confident that there's nothing wrong. Either call for the hazmat team, because we're highly confident their meters are calibrated, bump tested every day. At the very least, think about calling for a second meter from your station or nearby station to confirm that your meter is indeed working properly. When you see drops in oxygen levels, and I will tell you that I have not put a hard number on it because of the natural fluctuation between 20.8 and 21. Where is the right number to put a mandatory SCBA use? Right now, I'm in the 20.6, 20.7 range. But I will tell you that a drop from 20.9 to 19.5 is too far, right? And that's when the meter goes alarm. That is too far, too long to wait before you mask up. You're dealing with about 70,000 parts per million of something else, and that's not a chance to take. So everything here requires some judgment, yeah? And we expect you guys to exercise judgment day to day. What I'm telling you is you start seeing oxygen levels drop 20.7, 20.6. If you don't have your air pack on your back ready to quickly dom that, you should think about it. Now, that brings up another interesting point. And I don't know, I'm sure that there are instances of this in Montgomery County. But the one case that I'm familiar with was in Prince George's County. It was at the Washington Post facility, and it's where they printed the newspapers, right? One of the 3 or 4 places where they actually took these huge rolls of newsprint. They were brought in on trains. The train tracks actually went through the building, offloaded, and they were huge. They were probably 50 feet in diameter, a couple of tons. And if those things ever got wet, those tightly wound sheet rolls of newsprint, they would explode with, force of a detonation. So the fire protection in that building was carbon dioxide. There were 17 tons of carbon dioxide in a rooftop unit. And given the amount of laboratories and other research facilities in Montgomery County, I rest assured that there are other places that use carbon monoxide, or correction, carbon dioxide to as a fire suppressant agent instead of water or some other, halogenated agent. What's interesting is the team went in to investigate an activated alarm, automatic fire alarm, and they bypassed the annunciator panel. And they were walking down the building looking for the fire that wasn't there. And they all started to feel funny. And they couldn't figure out what was going on. And like one dude almost passed out. And they got the sense that they should mask up, right? So they mask up, they put the air packs on. We find out later that there had been an accidental discharge of the carbon dioxide sensor or the carbon dioxide suppressant system. And those guys were probably walking around 17, 18% oxygen, which is why they started to feel funny. You would not have seen the carbon dioxide on your CO meter because a CO sensor, the chemistry doesn't work for carbon dioxide, but you would have seen that drop in oxygen. Again, to emphasize the point, where you see oxygen dropping, don't wait to 19.5% to mask up. Wanted to hit this cleaning thing too, again and again. Please, please, please. We've issued guidance on how to clean these meters, and we want you to follow that guidance. Yeah. And then don't use alcohol because you kill the sensors. So that represents the end of my presentation, just under an hour. So I'm feeling pretty good about that. We have 28 people here. I have a few more minutes. We can try to answer a question or two if there are questions. I'll give you guys a few minutes. I don't know if you can raise your hand on Zoom or not, but let me do this. Let me cancel the screen share. But if you have a question, now's a good time to unmute and ask your question. All right. Well, I don't know about you, but I don't hear any questions. So with that, I will wait, hold on a second. Let me see it. Yeah. So I'm just double checking that you have the ability to unmute yourselves.